The ladies were protesting about having American missiles on English soil. And it was a peaceful protest. All they were doing were camping outside the perimeter of the American base. There was no violence, no swearing, no shouting. It was a peaceful protest. And it was found that from the American base, the ladies were being microwaved, and it was actually measured.
Hi. Last year, we did a series of videos on LRAD, L-R-A-D, which stands for Long Range Acoustic Devices. It's a beautiful fall day here in New England. Recently, there's been a lot of interest in this because of all of the protests that are occurring around the world. And we've gotten a lot of questions as to whether or not some of the injuries that have been reported by people who participated in those protests, whether or not they could be due to an LRAD device. By definition, an acoustic device attacks the ear. The target is the ear. Whether it's through the ear canal or through the bones around the ear, it is an overwhelmingly painfully loud sound. It isn't stealthy. And the kinds of injuries that were reported, I've seen the videos and I've read the reports, they're not consistent with that. There's facial swelling, there's swelling of the lips, the eyelids, there's burns, blisters. An acoustic device is not going to do that. Even if you could up the energy to incredible levels to injure the skin or burn the skin, you'd have to use so much power that you'd make everybody instantly deaf. So it's unlikely that it was an acoustic device that did that. The injuries are also not consistent with chemical burns. Any kind of an irritant that could irritate the skin, injure the dermis to the point that you form burns, is going to do an order of magnitude more harm to the mucous membranes in the eyes, the mouth, the respiratory tract. You have coughing, people would be complaining of shortness of breath, and you don't see those kinds of reports. The injuries are, however, consistent with a microwave attack. And there are weaponized microwave systems designed for what's called LRAD, which is the same series of letters but stands for Long Range Area Denial. They're built by military contractors. There's even some websites and some YouTube videos by some military contractors who produce these systems. Raytheon is one. So they do exist, and it is plausible they may have been used in some of these protests. I find that very troubling because even the most powerful microwave weapon is not a battlefield weapon. It won't take out a T-90 tank. It won't even be able to take out a few infantrymen with high-powered rifles because the range of these devices is rather limited. So these devices are actually used for lightly armed or unarmed civilians. They're used by governments on their own citizens, and that's what I find so troubling. So today what we're going to do is we're going to cover the use of microwaves, their interaction with different types of materials, and then jump right ahead to a means of defending yourself or defeating a microwave attack. Now, the way microwaves work is they interact with water molecules. All electromagnetic radiation consists of photons and an associated electric field, a sinusoidal varying electric field. And because water molecules are dipoles, they're asymmetric. When a microwave interacts with a water molecule, it causes the water molecule to attempt to flip to align itself with that varying magnetic field. In a microwave oven, that field is varying at about 2.5 gigahertz, or 2.5 billion times per second. That flipping of the water molecule creates frictional heating, transfers that heat to the non-responsive solids in the food, and cooks your dinner. The problem, though, in terms of a weapon system, is that the microwaves interact at that frequency moderately or modestly with the water. It takes a lot of water molecules to absorb some of that energy of the microwave as it's penetrating, and so the microwaves penetrate deeply, which is good if you're cooking a pot roast or a casserole. You want the heat deposited deeply within the food. But a microwave oven operates at a low frequency, while a weaponized microwave system operates at a far higher frequency, between 80 and 120 gigahertz. So instead of a 12.5 centimeter wavelength, the wavelength is down around 3.2 millimeters. Because it's flipping those water molecules 100 billion times per second, there's much more energy deposited in each water molecule. As a consequence, you don't need very many water molecules to absorb all the energy, and so all the energy is deposited in the outer layers, the outer 1 millimeter or so of the target tissue. From a weapons point of view, that's a good thing, because if you're trying to create pain or injury, it takes a lot more energy to elevate the temperature of a large amount of tissue if you have to go deeply into the tissue. There's a lot of mass there. But if all of that energy is deposited in the top millimeter or so of the very nerve-rich skin, you don't need much energy to cause the pain or the injury. The second advantage of the very high frequency of militarized systems has to do with optics. The ability for you to focus or collimate that beam of energy is related to the relative size of those optics compared to the wavelength. It's not the actual physical size of the reflective optics or the horns or the antennas. It's the size relative to that wavelength. So for a given size set of optics, the higher frequency has a shorter wavelength and can be better focused, better collimated, and sent farther downfield. So you're able in a weaponized system to send more energy farther, and you need less energy to cause the pain that's associated with that aerial denial. So this is probably within an order of magnitude of the same intensity levels of a weaponized system. So now that we've got this thing ready to go, let's see if we can block the radiation with a variety of different materials. Now you can see that this obviously glows like this. Let's see what happens if we put a piece of wood, 3/4 inch plywood, in front of the beam, like this. Now you can see that it glows, and you can see that it still glows. The wood does not block the radiation. Now, wood contains water, and water as a dipole molecule will actually flip in the electromagnetic field and absorb some of the energy. It will attenuate the beam, but there isn't a lot of water in plywood. And even though a high frequency, millimeter wavelength weaponized system will be even more attenuated by water, the fact that this doesn't work at all at this wavelength, probably not a good way to protect yourself. Now, another option is this material. It's the same stuff we built the poster board out of. It's a corrugated plastic material that's often used as a waterproof alternative to cardboard. And if we make the tube glow like this and place this in the beam, it doesn't do anything. Now, if we replace that with a very heavy piece of fiberglass, this material is so strong, it's an epoxy fiberglass composite, that it will stop a number of different calibers of bullet. But you can see that it doesn't stop the microwaves. The reason none of these materials block the microwaves is because, other than the example with water, which has a polar molecule that can flip back and forth and convert the energy into heat, none of these other materials include any kind of free polar molecules that can interact with the beam. And because they are not electrically conductive, they will not reflect the beam either. It will transmit right through them. So what happens if we get something that is electrically conductive? Okay, you can see that we get the glow, and we also get the glow. As you can see, the Kevlar does not block the radiation. And the reason that is because in the example with the wood, we had a little bit of a polar molecule which is able to attenuate the radiation by interacting with it and absorbing some of it and converting it to heat. But in all of these other examples, these materials do not contain freely mobile polar molecules. They can't interact with the microwaves, and therefore they don't attenuate it. And because none of these materials are electrically conductive, they won't reflect the energy either. You need an electrically conductive material in order to reflect an electromagnetic radiation like microwaves. So let's see what happens if we change gears. Okay, this is called ribbon toe carbon fiber cloth. The reason they call it ribbon toe is they flattened out the individual little yarns in order to make the material extremely thin and decrease the sort of zigzag of the fibers. This makes this material extremely stiff and extremely strong, and is often used in aerospace applications and very high-end sporting equipment. The bottom line, though, is it's carbon fiber, and even though it's only 250 microns thick, it's electrically conductive. So let's see what happens. Now, as you can see, the beam in front, but nothing in back. In front, but nothing in back. And in fact, nothing over here, but you can see it's reflecting over there. And that's because this is an electrically conductive medium. This material is graphite film. It's also 250 microns thick, and it's formed from hydrostatically pressed graphite. It's often used as a heat spreader in electronic equipment, as well as high-temperature gaskets in furnaces. It's also an excellent material for exfoliating graphene, as we'll show you in a future video. But the bottom line is this stuff is inexpensive, it's very flexible, it's soft, and it's electrically conductive. Now, once again, glows, but it doesn't. Glows, but it doesn't. And as you can see, it reflects the energy because it's electrically conductive. Now, a lot of people ask us whether or not there would be a way for them to protect a room, either in a home or an apartment, from electromagnetic radiation, including microwaves. And there actually is a good way to do that, taking advantage of the idea that a conductive layer, electrically conductive layer, will block the microwaves and other radio waves. So what you can do is you can purchase this material. We use this in a lot of our projects. It's rigid polyurethane foam insulation, and you can get it in huge sheets at big box stores. It's inexpensive, and it has a thermally conductive barrier in the polyurethane foam. But to enhance its thermal barrier effect, it has a sheet of aluminum on one surface that acts to reflect thermal infrared, increasing the insulation properties. But the aluminum is electrically conductive. So let's see what happens with this in a microwave beam. All right, let's see what we got. A lot of power. No power. A lot of power, no power. And it reflects, if you look, because of the angle, there's very little over here, but as you can see, it's reflecting the beam out this way. And nothing. And power. So this is a very effective means of blocking electromagnetic radiation. So the way you would use this material is typically as an insulating barrier. You would cut it into segments that would then be placed between the studs in a stud wall. And the aluminized film will block electromagnetic radiation. But as we demonstrated, the wood won't. So if you're going to try to create a true Faraday cage, surround yourself with an electrically conductive material, you're going to want to wrap something around this, either a little piece of sheet metal or some aluminum, or you may be in a building that has aluminum studs. But you always want to keep a complete barrier, either always in front of the studs, always completely behind the studs, or you're going to want to wrap this thing up. Also, don't forget the ceiling and don't forget the floor. In any case, we also want to try to find a way to protect you if you're mobile and you're not just building a building. Let me show you how we might be able to do that. So based on electrical conductivity, we had a large number of people commenting and questioning whether or not we could use something like this, an emergency blanket, often called a space blanket or a thermal blanket, as a means of protecting ourselves. It'd be wonderful because it's nice and light, portable, and inexpensive. The question is, does it work? Now, this material is based on an extremely thin layer of a polyester film, great insulator, very strong plastic, on top of which they've placed a chemically vapor deposited layer of a few atoms of aluminum. And as a result, the material is electrically conductive. Now, if you look at the meter right now, this shows you when you've got electrical conductivity. If I touch these two probes to the surface, you can see that it's electrically conductive. However, if I turn the surface upside down and we do the same test, on the backside, it's not electrically conductive. So the aluminum coating is placed only on one surface. So we got a lot of suggestions or questions from people as to whether or not we could develop a method of detecting the beam that's a little bit better than carrying around a fluorescent tube. And I think I came up with a pretty good solution. This is our old polycarbonate riot shield that has a aluminum grid on the front of it that blocks the microwave radiation. And as you'll notice, I'm walking right in front of the 1200 watt beam. And as you can see on the front, we have these little detectors that are going off based on being hit by the beam. It works. Now, the suggestion was made that we should use LEDs, maybe take advantage of the electric field that's built up in the conductive layer in order to drive an LED detector. The reason I stay away from that is because LEDs pose a couple of challenges there. First of all, an LED wants to run on polarized output, either continuous wave or pulsed DC, and this is generating an AC current. In addition, LEDs have a rather narrow voltage range of operation. Too low, they don't work, and not much higher, and you damage them. So because of that, I decided instead to use neon bulbs. These are little neon indicator lights, the same thing you put on the front of an instrument that you can hook up to AC in order to show that the power is on. What's nice about these things is they're super robust. These can be blasted with 10,000 volts, and they'll still continue to work. In addition to that, they work on AC, and these devices do not require any kind of controlling electronics because the tiny little leads that extend out of the bottom that you can only hook up to a power supply act as antenna. So you don't need to have any kind of electrical connection to the grid or the material that's blocking the radiation. That's convenient if